Okay, folks, the sponsor has spoken. We are ready. Who's our sponsor? Our sponsor is Oscar Mayer. Oh, I wish I were an Oscar Mayer wiener. Everyone would be in love with me. Okay, I'll stop. I know. I'm sorry. Okay. Tell your stupid jokes. It's better than your singing. Whoa, Billy. Whoa, come on, man. After all we've been through, that's harsh. I feel bad about myself now. Okay, let's get going. What was I going to do? Oh, I know. I remember now. We just finished up the video on work with a gas. Okay, work with a gas. Expansion and contraction of gases, that's movement, and you got to put pressure on them in order to get them to expand or contract. And that's our equation for work. Okay, we'll come back to that, that's for sure. But now let's take a look at the first law. The first law of thermodynamics. Oh wait, there is a zero law, by the way, called the zeroth law of thermodynamics. It's kind of weird because you would think the zeroth law would be the first one, and it would be called the first one, and then the second one would be the first one. Instead of the zero, it's confusing. I know it's confusing, but there's actually something called the zeroth law, the zero law. Let me just go through it real quick. It's relatively easy. Let's say you have object A, block A, and it's in contact with block B, and that's in contact with block C. Let's say these are perfectly insulated, no heat can get in or out of the system, there's my insulation around it. And let's say that block A is at 20 degrees Celsius, block B is at 20 degrees Celsius. If these are all in thermal equilibrium with each other, what is the temperature of block C? Yeah, you got it, you know it, you say it. It's 20 degrees Celsius. What that says is if A is in thermal equilibrium, you remember that means same temperature, in thermal equilibrium is block B, and B is in thermal equilibrium with block C, that would also mean that A is in thermal equilibrium with block C, which is kind of logical, it makes sense. It's one of those little logic things. Yeah, if you're the same as you, and you're the same as you, then you gotta be the same as you. That's it. It just means things at the same temperatures are in thermal equilibrium, and if one is equal to the other one is equal to the other one, this one's equal to that one. Okay, that's the zero law. Now, we're not going to do anything more with that. It's just kind of like, oh yeah, that makes sense. Kind of a law. Let's look at the first law. That's the one that we really want here today. The first law of thermodynamics, which is really the second law because the zeroth is the first law. Again, it's kind of confusing, I know. The first law of thermo, you know. You don't know you know, but I'm going to show you that you know that you know. You've heard of it before. In words, the first law is conservation of energy. That's the first law in words. Energy cannot be created or destroyed, only changed in form, okay, in ordinary chemical reactions. In nuclear reactions, boom, yeah, we can change energy, mass to energy, energy to mass. Yeah, but in normal chemical reactions, we know that the conservation of energy is going to hold. It always does, will. Trust me, it's a law, okay? It's never been shown to be anything different. If you show it to be something different, let me know, let me in on it. We'll become bazillionaires, okay, you and I. So we all know that physics needs an equation for everything. Yes, you do, you know that. So we know that the first law is conservation of energy, but what does the equation look like? Okay, this equation, sweet, looks like this. The first law equation looks like delta U equals Q minus W. Actually, I'm going to change that. We're going to make it Q plus W. Wait a minute, you can just change it like that? Well, actually, sometimes you'll see it either way. Sometimes you'll see this as a plus or a minus. It depends on whether or not you defined your work. Remember from the last video, we said that work done on a system is positive and work done by a system is negative. It makes sense. Okay, if that's the case, then we use this one here. There was an old way of expressing, I say old, I mean as of 2014, okay, physics, AP Physics anyways, started using this version. There was an older version where this was a negative, and then you'd have to switch the on to a negative and the by to a positive if you're using this as a negative, and it was a little confusing for people, so I might even be confusing you now. All right, bottom line is, using on as a positive, by as a negative. That's her equation, okay? And in fact, if you looked on a sheet, it'll say that version. Okay. So this is the first law of thermodynamics. What does it say? Well, we know this is heat. You do. You know that. You know this is heat. And you know W is work. What is this? Okay, that is change in internal energy. Internal energy. So U is internal energy. Internal energy. What's that? What's internal energy? That's the total amount of potential and kinetic energy a system has. A system is whatever you define it to be. You're a system. Okay? I'm a system. So my total amount of kinetic and potential energy would be my internal energy. So the internal energy is total PE, potential and kinetic energy. It's the total of your energies. So now what this is really saying is, this is the bottom line here. You look like a bottom line kind of group. Yes, you do. Yes, you do. You look like this. That's what you look like. Bottom line. Get it? It's a bunch of lines in the bottom. That's what I was getting out of you there. Okay. I don't need you. I got that thing. Now. Bottom line. Okay, so bottom line is this, that if you want to change the energy of a system, you got two choices. You can do work on it, or have it do work. Oh, here we are. Work, have it do work, or add heat to it, or have heat taken out of it. The two ways you can change the energy of a system are by heat and by work. Okay, let me give you a little example here. Let's say that we have a beaker of water. Nice, good old, high quality, made in America water. And maybe you've got your beaker of water sitting on a hot plate. Okay, here's a hot plate, put some legs on it, get some buttons, make it look like an official hot plate, whatnot, little lights and stuff. And then, you decide to increase the internal energy of this water. You want to heat it up. Now you might say, well, just turn up the heat, right? And put wiggly lines. That's universal for heat, wiggly lines, arrows going up. So yeah, what we're doing now is you turn on the hot plate, certainly you're adding heat to it. You're adding heat to the system, and that's certainly going to increase the internal energy of that water. It's going to make it warmer. But you can also do something else. Yes, you can. You can actually maybe take like a spoon or something. Well, let's see if I can draw a spoon. That's a nice spoon. Yes, it is. And you could twirl it. Twirl the spoon in the beaker. You're doing work on the system, that being the water in this case. You're doing work on the system. If you're mixing up the water, you are doing work on the water. What's that going to do? That's positive work. Positive work will positively increase the internal energy of that water, making it warmer. So you can do two things at once. You want that water to get warm faster because you want to make those sweet, sweet ramen noodles? Well, crank up the energy, heat, increase that energy. Sure, it's going to increase the temperature. And then do some work on it. Come on, get your back into it. Put your back into it. Do it. That will do it even faster because you're adding energy. You're adding energy to the system. Remember, joules, energy to the system. You're going to change its temperature. In fact, let's see. I don't have a water bottle with me. Dang it. I always have a water bottle with me, but I don't have a water bottle with me today. Oh, well. Try this at home. Not for professionals only. Okay, I have my students do that when they're here. I take this water bottle, it's half full of water, and shake it. Shake, 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 shake your booty. Shake your booty. Casey and the Sunshine Band. That's for you, Casey. Oh, Sunshine Band. Now, don't put your hand over the water because you'd be increasing the temperature of the water through your hand. Put it like on the top of the bottle and shake it. And do that for like 3-4 minutes. You will start to get a little tired. But take the temperature before and after shaking. It will go up. Trust me, you. Don't believe me. Try it. I'm wearing a stupid shirt. Try it on your own. You can get the temperature of that water to increase just by shaking its booty. So you can get the temperature of the water to increase by doing work on the system. That's positive work. You'll get it to warm up. All right, you're moving those particles faster. Okay, increase in temperature is related to kinetic energy. Increase in kinetic energy, you're increasing the temperature. All right, okay, all right. So 2 ways to increase something's temperature. Add heat to it, have it do work on it. Do work on it. Okay, shake up that water. All right, so let's see. So this is going to be a change in joules. Again, in joules, joules everywhere, not a drop to drink, okay? Rhyme of the Ancient Mariner. We've all read it. We all know that you can't drink that water, okay? It's salt water, okay? You all know what I'm talking about, right? All right. Let's see. Let's do let's do a math example. Math example here for you. Let's go back. Actually, I'll erase this, get this out of the way. And now I've got my water here, and I was, increasing the heat into it. Let's say my heat into this container of water, I add 3,000 joules of sweet, sweet heat energy. At the same time, I was mixing it with that spoon. That's not a good spoon. Oh well. Mixing it with this spoon, and by mixing with the spoon, I do 1,000 joules of work on it. Okay. What is my overall internal energy change? This is not difficult, people, not difficult. Okay, so 3,000 is my heat. 1,000 was the work that I did on the system. Then the change in internal energy, of course, would be 4,000 joules. Now that's going to increase its temperature. How much? That depends, okay? It depends on how much stuff is there. Is there a lot of water? Okay, and is it water? If it's not water, it's going to have a different effect on it because of its specific heat capacity. So that will change its temperature. That certainly could be a next question as to what is the new temperature of this water, if it's water, or whatever it is, by doing the work and adding the heat to it. All right, so we can calculate that by using m delta TCP. So this can then be set equal to m delta TCP in order to get the change in temperature. Okay, lots of fun things that we can do like that. So I'm going to keep this video a little shorter today. Instead of like 25-minute videos. I know you guys hate those, but I have fun. Okay, that's the only important thing. So, okay. Oh, we got to do some vocabulary with this. Very important vocabulary. That's next after our next sponsor's commercial break.